Okay guys, here is another question on radioactivity. It looks a bit challenging, yeah, sure. I'm going to share my understanding of it. Of course, there are different ways the same question can be answered, okay? Now, if you find my own method easier and understandable for you guys, kindly study it, like, share, and recommend the video to your friends and classmates, okay? So here it is. A piece of ancient bone from an excavation site showed carbon-14 activity of 9.5 disintegrations per minute per 1.0 exponential minus 3 kilograms. If a bone specimen from a living creature shows carbon-14 activity of 12 disintegrations per minute per 1.0 exponential minus 3 kilograms, find the age of the ancient bone. Now guys, you need to pay attention to the statements. To find the age of the ancient bone, simply ask that we calculate the time. It's just to calculate time, not half-life, okay? Simply to calculate time. Okay, of course we know the half-life was given as 5,572 years, so we're calculating the time of disintegration. One important thing I want to point out to you is this: when you see a question that has to do with a living creature, if that question has anything to do with a living creature, okay, know that the disintegration or amount of material remaining in the living creature is disintegration at the beginning. Just take note of that. If your specimen has anything to do with a living creature, its disintegration or amount of material remaining or decayed means material at the beginning. So any other disintegration has to be the disintegration for the given time in question, okay? So having said that, let's see how we can apply this to solve this problem. Okay guys, let's look at this, okay? The first thing we notice is half-life. It was given as 5,572 years. Okay? Now remember I said the disintegration or the activity or number of material remaining or decayed in a living creature means the disintegration at the beginning. So you can actually use this representation and subscript not, or you can put it this form. Whichever understanding that makes it easy for you. Okay? Now you look at the question, we're told it was 12. Now, per time per 1.0 exponential minus 3. For the two cases, the masses were the same, so we don't have to divide by mass. Okay? And now, after the time in question, the activity n, which you can decide to use this expression if you so desire it, disintegration at a particular time t was given as 9.5. Okay? The question now is, what can we do? There's this formula in radioactivity that activity at a time is activity at the beginning divided by 2 raised to the power n. Now, you know we have activity at the beginning to be 9. Okay, at a time is 9.5, at the beginning is 12 over 2 raised to the power n. So we can make 2n, 2 raised to the power n, change of subject, we'll have 12 over 9.5. And when you divide this, we'll get a value about 1.2632. Now, how do we find small n, which is number of disintegrations? Okay, you take log of both sides. So log 2 raised to the power n is equal to log 1.2632. You remember in log they say log b raised to the power a is the same as a log b, right? So using that idea, you see that n log 2 is equal to log 1.2632. So number of disintegrations becomes equal to log 1.2632 divided by log 2. So all you have to do is press those in your calculator, okay? Press those in your calculator and you get your number of disintegrations to be approximately 0.3370. Having done this, you remember again there's another expression that says time of disintegration is equal to number of disintegrations multiplied by half-life. Since we're looking for this time, which should be the age of the ancient bone, so number of disintegrations is 0.3370 multiplied by half-life 5572. You simply multiply those in your calculator and you have the age to be approximately 1,878 years. Now, if you appreciate this method, okay, it's cool. You can use this approach and you get this. Now, what if there could be another way? Remember I said there could be different ways it can be analyzed by different people. I'll definitely give you a correct answer. Now, let's look at an alternative method. So, in this alternative method, okay, you simply remember that our half-life is 5,572. We can actually find the decay constant using ln 2 over half-life, which is 0.693 over 5572. So we'll have our decay constant. When you press those in your calculator, you have a value of about 0.0012437 time, okay? That disintegration per time. Now, this is not what we're looking for. We're looking for the time of this disintegration, which will give us the age of the ancient bone. Now, do you remember the expression that activity at a time is equal to activity at the beginning exponential minus decay constant multiplied by time? This small t is the age of the ancient bone, which will be the time for disintegration in question. Of course, this is activity or disintegration at the beginning. This is disintegration within the time of interest. Now, what do? We simply look for a means to make this t subject of the formula. Now, I don't want to substitute all the values in now. Let me try and make t subject of the formula. What will I do? I will divide both sides by n naught. This will cancel this. So I'll have n over n naught equal to exponential minus lambda t. Remember, I want to make t the subject. How do I remove this exponential? I will take ln of both sides, natural log of course. Just saying, like you want to say, take log of both sides. Log anti-log will make this disappear. So ln and exponential will make this e to leave. So you take natural log of both sides, that's ln n over n naught is equal to ln exponential minus lambda t. Of course, this ln will cancel this e. So we have ln n over n naught equal to minus lambda t. So now we can make t the subject of the formula. So it shows that this t is ln n over n naught divided by minus lambda. Okay, now we can easily substitute. Our n was given as 9.5 On your calculator, just check 9.5 divided by 12. Then press ln of that. Okay, let me say this is ln 0.79167 over minus 0.000124337. So we still have t to be. Now we can press ln of 0.791667. When you press that in your calculator, you have minus 0.2336. Of course, this is an approximated value. Divided by minus 0.00124337. When you check this division in your calculator, you have time, which is the age of the bone, to be approximately 1,878 years. This equally agrees with the same answer we got using the first method. Now, what is very important here is this, guys. Look at the two approaches I've used. Which one do you find easier? Which one was clearer for you to understand? Of course, if you find them interesting, kindly share with your friends, recommend the page to your friends, and of course, share.